Hello everybody, and welcome to the second video of the course. As with the first video, please just ignore this date down here. I don't know how to get rid of it. It's just the date when the slides were created. In this video, we simply continue the thread of thought that we began in the last video, and I'm just going to continue talking about arithmetic, so operations you can do, and numeric data types, so variables of type int and float, etc. So just to recall what we did last time, we defined the data types integer, long, float, and double, and we've just pointed out that C++ recognizes the addition symbol, the subtraction symbol, and the multiplication symbol. So we introduced the 4 numeric data types that we need for the course, and we pointed out that arithmetic exists already built into the language. You don't have to tell the computer how to add. It already knows how to add. This time, we're going to start where we left off with going to division. That's sort of the first natural operation to pick up with when you end with multiplication. And then we're going to do some other operations. This probably means nothing to you, but we're going to talk about modular reduction, which is a kind of division, I suppose, taking square roots, taking powers in general, and variable manipulations. So let me just go straight to the compiler, and once again, this is the bare bones of any program you will have. You will always start with this. Okay, so you always have these 1, 2, 3, 4, 5 lines of code here. And as with last time, the code you're going to write is inside these main braces. So inside this opening brace and inside this closing brace. So what I want to start with is just various things you can do with variables. So let me start with an integer variable, and let me start by giving it a value of 3. So, if I tell the computer, print to the screen what A is, the computer will oblige, and it will tell me that A is 3. Right, so suppose that right now in the code, though, I write this. I say A is, equals is in English. A is A plus 2. Now, if we were in class, I would ask you now, what happens here? When I print A to the screen, what value appears? And there are several ways to think about what happens. And first, let me remind you that the computer reads from top to bottom. So it starts here and it says to itself, okay, Dr. McCune created a variable of type called A of type integer. So I've created a storage space for a whole number. And then the next thing I do is I give that whole number variable the value of 3. So right now in the code, A literally is 3. That's the value in that storage space. And then the next thing I do is this line of code. And then after that, I'm going to print the value of A to the screen. So at the very least, you might think that A is 3 right here, but probably not. This line of code probably does something. And what it does is, when you have an equation like this, where you have the same variable on both left and right like this, what I'm saying is, take this expression here and overwrite the old value for A. So right here in this white space in the code, A is 3. What I'm saying right here is, okay, A is 3, so take 3, add 2 to that, which is 5. Now take that 5 and overwrite that 3 that used to be there. So what you're literally doing is, you used to have a 3 in this box, right? A is like a box, an integer box. And I'm saying, take that 3 out, add 2 to it, and put the result back in the box. So A should now have value 5, and it does. So, you can do this with anything. If I now write, okay, A is 2 times A. Then again, what's happening is, right here, A is 3. Right here, you're taking that 3 and multiplying it by 2 for a result of 6. So the end effect of all this is you are taking the 3 out of the box and putting a 6 back in there, etc. So this works exactly like you think it does, no matter what you put here. So this now is slightly more complicated, but, A is 3. So 3 times 3 is 9. Plus 6 is 15. So what I'm saying is, take that 15 value and overwrite the old value of 3. So take 3 out, put a 15 back in the box. So when I ask the computer what's in the box, it prints 15 to the screen. So this is really the only variable manipulation that we care about right now. Just I want you to know that you can overwrite values of a variable using equations that involve the variable itself if you want to. So what's on the right-hand side will get overwritten onto the left-hand side. Okay, so before we leave this topic though, I do want to point out that, in general, equal signs are symmetric. In other words, like in math, you can write either x equals 5 or 5 equals x, and they mean the same thing. But this line of code here, this line of code right here, is not the same as this. So you can't just switch the values of the equal signs. So notice right here, the computer, it lights up red right here. It says, I don't know what you're doing. I'm confused. And if I try to run this, it won't even do anything. Notice all I've done is switch the sides of the equal sign. So in math, you would expect that to not give you any problem at all. But in C++, you do get a problem. Because when you have equations like this where you have a variable on one side and itself on the other side, now the meaning is take what's on the right and put it into the left. So take what's on the right, whatever that value is, and that's now the new value inside this storage box right here. So in any case, you can't switch the sides of the equal sign. Okay, now there are a couple of equations like this that come up often enough that there are special lines of code for it. So consider a line of code like this, that a equals a plus 1. So all you're saying in English is take the value of a and up it by 1. So increase a by 1. So if I run this, I should get a 4 right there, and I do. For whatever reason, the designers of C++ wanted a shorter way to write this equation. So instead of this, they write a plus plus. So a plus plus means the same thing. It means take the old value of a and up it by 1. So when I run this code, it will do the same thing. Right? So a was 3, now a is 4. And similarly, this line of code right here says take the value of a and decrease it by 1. So if I run this, my 3 will become a 2. So again, for whatever reason, this comes up often enough that the designers of C++ didn't want to write this equation, which has 6 symbols in it. They shortened it to a minus minus. That has the same effect. So the 3 gets down to a 2. Okay, so those are all the variable manipulations I wanted to talk about. You can have equations involving the variable on the left and on the right, and what happens is the right-hand stuff overwrites the value of the variable, which is on the left-hand side. Okay, so now let's move on to more operations. Okay, so this time let's start with division. So I'm sort of doing this list backwards. I've done variable manipulations. Let's now move on to division. So division works, like division. You all know what division is. So if I ask you, what gets printed to the screen here? I'm telling the computer, please print for me the result of 6 divided by 2. So what do you think will get printed to the screen? Well, you'd be crazy not to say 3, wouldn't you? 6 divided by 2 is indeed 3, and that's what gets printed to the screen. Okay, now let me do the same thing. And now I want to print to the screen 7 divided by 2. And as we all know, 7 divided by 2 is 3.5. It is 3.5. So if I ask you what gets printed to the screen here, you would be crazy not to say 3.5. And yet, in this case, you would be wrong. If I ask the computer to divide 7 by 2, it prints 3 to the screen. Okay, why is it doing that? Why is it giving you the wrong answer? Because we all know that 7 divided by 2 is not 3. 7 divided by 2 is 3.5. So first of all, let me just say that this little feature of C++ will trip you up at some point. You will indeed forget that the computer does this sometimes. So let's just establish that as a baseline. That will happen to you. So prepare to be annoyed by this, I guess is what I'm saying. This is kind of obnoxious. But what the computer is really doing is it looks at this expression and says 7 is a whole number. 7 is an integer. 2 is also an integer, isn't it? 7 and 2 are both integers. And when I take an integer and divide it by another integer, the computer wants to give me an integer back. In other words, if you start with 2 whole numbers and you do something to them, the computer wants to give you another whole number back. So what happens is the computer does 7 divided by 2 and gets 3.5, but then the computer says, oh, but he gave me 2 whole numbers, so he must want a whole number back. So it takes that 3.5 and just truncates off the decimal. So it just forgets about the 0.5. This is known as integer division. This is what happens when you take 2 whole numbers, divide them, and get another whole number. If you insist on getting a whole number back, then you simply lose the stuff that comes after the decimal point. Okay, so this is obnoxious on some level, that the computer does this. And of course, if I put like an 8 right here, 8 divided by 2 is a whole number already. The computer has no trouble with that, But again, like 9 divided by 2 is not a whole number, but the computer will try to give you one, right? 9 divided by 2 is 4.5. It will give you 4. So the reason it's doing this is because on some level this idea of integer division is useful. If you live in a world where you can't divide things into smaller pieces, then integer division is what you have to do. So for example, consider a scenario where you have $9 and a candy bar costs $2. Okay, these are kind of expensive candy bars. Suppose I ask you, how many candy bars can you buy? I suppose you could say to me, well, 9 divided by 2 is 4.5. Therefore, I can buy 4.5 candy bars. But I would say to you, no, you can't. You can't just take your knife to the grocery store and cut candy bars in half. You can't just take the product and divide it into smaller pieces. So if you have $9 and they each cost $2, you can buy 4 of them. And then you have $1 left over. So integer division is useful when you can't actually divide things into smaller pieces. And that's why the computer does this. Now, if you want the real answer, if you want the actual division, you have to do this sort of obnoxious little thing, but it fixes it. This is called float casting, or casting to float. So what you're doing is you're telling the computer, don't think of 2 as a whole number anymore. Don't think of 2 as an integer. Think of 2 as a decimal. And now the computer says, oh, whole number 9 divided by decimal 2, okay, fine. He wants the actual result, which is 4.5. So since you aren't dividing 2 whole numbers anymore, it doesn't worry about truncating the decimal anymore. It gives you the actual result. So you can put this float on either the numerator or the denominator. It doesn't matter. As long as you cast one or the other, it will give you the result that you want if you want the actual division. Okay, so that's how division works in C++. And so let me just give you one more example. Let me just create 2 variables here. So that A is 5 and B is 3. So again, if I asked you what this line of code prints, let's see, A divided by 3, if you didn't know any better, you would say, I guess it's going to print 1.666666667, because that's what 5/3 is. Okay, but it's not going to print that, oops, by B. Because again, A and B are both defined as whole numbers. So it takes that 1.66666, chops off everything after the decimal point, and just gives you 1. But if you tell the computer, look, for the purposes of this division, please think of A not as an integer, but as a decimal, now notice what it does for you. Now it actually does the the division. It has to round, of course, because it can't type infinitely many 6s, but it does closer to what you want. Okay, so that's how division works in C++. You can divide variables like this, you can divide just numbers, whatever, but just be aware that when you do division, if both top and bottom are integers, are whole numbers, the computer will do integer division and it will truncate after the decimal point. Okay, so let me go back to my list here, check and check. Now let me move on to this thing called modular reduction. Okay, it sounds fancier than it is. So let me let me just write a line of code here, and then let me explain what it means. Okay, so if I asked you, what do you think this means? You would say, I have no idea, because percentage symbol I have never seen used before as like a plus or a minus. Okay, I have no idea what that means. So let me tell you what it means. Whenever you do something percentage something, what you're doing is you're telling the computer, please take 6, take what's to the left of the percentage symbol, and divide it by 3 for me, please. Okay? But don't give me the result of the division. If I wanted 6 divided by 3, I would have written 6 divided by 3, wouldn't I? Okay, so you're not just going to do division, computer. What you're actually going to print to the screen is the remainder when I do the division. So hopefully the word remainder is familiar to you. You know, it's a word you learned in 3rd grade or whatever, but you know, it's going to print to the screen what's left over after you do the division. So when you take 6 and divide it by 3, I hope all of you know that there's nothing left over. There's no remainder. So what's going to get printed to the screen here is 0. So just to sum up here, when you do something percentage something, you are saying take the left-hand guy, divide by the right-hand guy, and give me the remainder of that division back. Don't give me the actual division. Don't give me the, what's the word? The quotient, I guess. Don't give me the quotient. Don't give me the product of the division. Give me the remainder. So, for example, if I change that 6 to a 7, I hope all of you know that when you divide 7 by 3, you have 1 left over. So 1 is printed to the screen. 8 percentage 3 means take 8, divide it by 3, give me what's left over. 2 is left over. Okay, and so on. So that's how the percentage symbol works. It's a remainder operation. And again, this is the technical term here, modular reduction, but just think of it as calculating remainders of division for you. So if we were in class, I would now ask you to predict what this is. When you take 3 and divide it by 8, what's the remainder? And if you think back to the actual definition of remainder, when you take 3 and divide it by 8, there's 3 left over. Okay, 3 goes into 8 0 times with a remainder of 3. So when you have something smaller here on the left-hand side, that something smaller is all that's left over. So if I change that 3 to a 5, whoop. You know, 5 divided by 8. What's the remainder? Well, the actual division value is 0, and what's left over is 5. Okay, 5 goes into 8 0 times with remainder 5. But if I do 8 percentage 5, when I divide 8 by 5, I get 1 with 3 left over. So 3 is the result. Okay, now, most students' reaction to this operation, this little percentage operation, this remainder calculating operation, the reaction is usually, well, who cares? That seems really kind of dumb to define an operation like this. I mean, we already can do division. What do I care about the remainder? And that is a good question. You know, like why this operation is useful is indeed a good question. And my answer to you basically is, well, you'll see later on why this is useful. Okay, it turns out to be extremely useful in things like dice throwing, which you might not expect. So in things like game programming, this operation is very useful. And we will see these uses later. But for now, let me just point out to you that anytime the number on the left is a multiple of the number on the right, so 10, I think you all will agree, is a multiple of 5. Anytime you have that, when you take 10 and divide by 5, you know, it's a multiple, so you have nothing left over. And when you have nothing left over, the remainder is 0. So whenever the number on the left is a multiple of the number on the right, you're going to get 0 out of that. So on some level, you can think of this operation as detecting for you when one number is a multiple of another. And that also has its uses, not just in this, you know, dice throwing thing that I didn't even explain anyway, but we'll see later. But think about, you know, writing a program that detects whether a number is prime. Now, I don't know if you remember what a prime number is, but a prime number is essentially a number with, I mean, it only has 2 divisors, 1 and itself. So it's not really a multiple of anything except for itself and 1. So you can see how an operation like this would be useful for detecting primeness, because this operation detects whether something's a multiple of something else. So if you're going to write a program that checks whether or not a number is prime, one thing you could do is just check what its multiples are. Or sorry, what it's a multiple of. So like 7 is only a multiple of 1 and 7. You can use this operation to detect that. So anyway, I'm introducing it now. By the time we use it, you may or may not have forgotten what it does. That is okay. I will remind you about it when we need it. Okay, now let's move on to square roots and taking powers. To take a square root or to take a power, you need to come up here to the very top and type the following line of code. What this is doing is it's tapping into a pre-existing library that's built for you. So we're not going to teach C++ how to take powers, just like we're not going to teach it how to add. So, the plus symbol is defined for you already. We didn't have to build that into C++. So taking square roots and taking powers like cubing or taking to the fourth, we also are not going to program ourselves. We're just going to tap into this pre-existing library. So to take a square root, it's pretty straightforward. You type in the number whose square root you want, and you do it inside the square root braces like this. So you literally just type square root of 5, and the computer knows what you mean. So here, let me forget about printing for a second. Let me just create a decimal, s. I'll let s be the square root of 5, and I'll print that to the screen. It will print the same thing, of course, right? But that's how square rooting works. So just like before, right, this little operator here, or this little equation here is saying, take the square root of 5 and assign it to s. Just like we had in the previous video. Okay, so that's how square roots work. They are pretty straightforward. How do you take a general power? How do you do, not square root of 5, but maybe 5 to the third, 5 to the fourth, whatever. Oh, but before I do that, I did want to point out something that I pointed out in the previous video, but again, you need to think about. You always should consider what this variable is being used for before you declare it, before you give it a data type. Because if I type something like this, int s, and then s equals square root of 5, the computer will run this. It has no problem with this. It's just that s is declared to be something with no decimal component. S is a whole number. So I'll leave it to you to guess what happens here when I run this, but you declare an integer s. You're saying that s is the square root of 5, but s can't really be the square root of 5 because the square root of 5 has decimal component in it. So what the computer will do is it'll say, fine, I'll try to put this number over here, but I can only give you a whole number, buddy. So that's what it does. It says, well, if you insist on the square root of 5 being a whole number, I'm just going to lose the decimal stuff. So again, it's kind of like the integer division thing. If you have integers floating around and you try to put decimals there, the computer won't play ball with you. It will just forget about the decimal. Okay, so now let me just move on to taking powers. So here's what you would think. You can already see the computer's yelling at me. See, here's what you would think you should do to take a power. You would think that you would just take the number and do the caret symbol to the power you want, because that's how it works on a calculator. For whatever reason, and it's not clear to me what the reason is because I'm not privy to the creation of, I don't know the thought processes of the men who created C++ or women, I'm not sure, but the people who made C++, I don't know what they were thinking. This is not how they defined how you take powers. They did something slightly more convoluted. Here's what it looks like to take a power. So power 5, 2. So the base is right here and the exponent's right here. So this is 5 squared right here. 25. So obnoxious. Okay, I will admit to you this is really obnoxious. And again, if you ever end up needing to take powers, you will probably write things like this in your code, and the computer won't compile it. Okay, it'll say, I don't know what you're doing. And don't blame me, blame the people who created this language for not doing the most natural thing in the world, which is just to use the caret symbol. But if you want PAL 5-3, if you want 5 cubed, you have to do PAL 5-3, and it will do it for you. Okay, so we've now covered most of the content of this video. Just to summarize here, you can overwrite variables with equations involving themselves. So a equals a plus 1 just increases the value of a by 1, but you can't switch the order of that equation. You can't switch the sides there. This line of code here can be shortened to a plus plus. Taking a and decreasing it by 1 can be shortened to a minus minus if you desire. If you divide two integers, so two numbers that have no decimal component, C++ will give you a whole number back. So 7 divided by 2 is 3 from the computer's perspective. This is called integer division. If you want to do regular division, you have to cast a float like we did. A percentage B gives you the remainder when A is divided by B. So 4 percentage 2 is 0, because when you divide 4 by 2, there's no remainder. Or to be more precise, the remainder is 0. But 5 percentage 2 is 1, because when you take 5 and divide it by 2, you have 1 left over. And notice this will be more and more useful as we move through the course. A percentage B is 0 if and only if A is a multiple of B. Or if you like, if and only if B is a divisor of A. I don't know which language you like, but B has to divide A, or A has to be a multiple of B in order to get 0 out of that percentage symbol. To take square roots or powers, you need that CMath package, that CMath library, just like we did. You have to include it at the top of the program, and you have to use PAL instead of the caret symbol. Highly obnoxious. Now, I want to finish this video by just writing a program that does something involving these things. So here's a sample program you could write. Let's write a program that lets the user enter the volume of a sphere, and the program will calculate the radius of the sphere, and it will print that result to the screen. So this is a program that lets you figure out the radius from a volume of a sphere. Now I should say here, before I do anything, that whenever you have problems like this, programs like this, I don't care if you know off the top of your head what the volume of a sphere is. I don't care if you know what the formula is. So if you don't remember what that formula is, your first step when being presented with a problem like this should be to just Google volume of a sphere. If you Google volume of a sphere, this is what comes up. Okay, so I don't care if you know this. The only thing I really care about is like really basic stuff like area of a rectangle, area of a circle, things like this. But anything else I don't care that you know. So before I write this program, let me just, as I did in the previous video, just outline how this program will go. So you don't have to do this for these like simpler, shorter programs at the beginning of the course. But once we start doing far more complicated and sophisticated things, I would always start by verbalizing what you will do. Okay, I would take the time to really say what you're doing, right? Say in English out loud what you were going to do, and then do it. Okay, it really streamlines your thinking to write a paragraph like this, or at least say it out loud. So here's what my programmer will do. I'm going to create a storage space for the user to give me the volume. Right, so let's the user enter the volume. So I'm going to create a storage space for it. I'm going to ask them for that volume and then get it into that variable I just created. So I create a storage box. I let the user put something in that box. I'm going to take that variable and divide it by the quantity 4/3 pi. I'm just going to isolate the r essentially, right? So move the 4/3 pi over by division and then cube root things to get the r by itself. So if you're confused by this sentence, all I'm saying is they're giving you a volume, aren't they? You're supposed to get an r value. So you get that r value like you would do in a 9th grade algebra class, right? You isolate the r. And then I'll output the result to the screen at the end. Okay, so let me just come here and see how that goes. So I didn't specify, but let's just assume that the user is going to give me an integer volume. Now maybe they won't. Maybe when you write this program yourself, you want the user to be able to enter a decimal volume. That's fine, I don't care. One thing to notice though is that even if the volume is an integer, the radius might not be. Because when you're doing all this fancy division and cube rooting, right? If v is an integer, it is highly unlikely that r will be an integer. So I'm going to create a storage space for the radius, but notice I use a float rather than an int. Okay, so let me just say that again because it's an important point when you're designing storage spaces. Even though your volume is an integer, there's no reason to expect your radius to be an integer because of the way you're going to find your radius. Okay, so that's why I created a float box, a float storage space for my radius. Now let's ask the user for their volume. Okay. Let's just make this look pretty by putting new lines in. So let's get it from them. Okay, so now the radius will be, let's see, what do I have to do? I have to take the volume and I have to divide it by the quantity 4/3, but remember 4/3, right? 4 is an integer, 3 is an integer, so you're going to have to do 4/3 like 4 divided by 3, where you're thinking of 3 as a decimal, okay? If you forget to do this little bit of code right here, 4 divided by 3 will be 1, okay? It will do the integer division there. So again, obnoxious. Times pi, we'll just call pi that. Okay, so the radius is the volume divided by this stuff, right? Divided by this, 4/3 pi, but you got to cube root all of that. Well, how do you cube root something? Well, you take it to the 1/3 power. And just to be careful again, I really want 1/3, don't I? Nothing else. Okay, so the radius is the volume divided by 4/3 pi, all taken to the cube root, which I may have said this too fast, but do you remember this, that taking a cube root is the same thing as raising something to the 1/3 power? Because if you don't remember that, that's fine. I just told you that's what happens. Okay, so now let's just have the program tell you what the radius is. Let's make sure that it's all spaced out nicely. Okay. So here's a program that does that, right? I ask for the volume, I get it. I calculate the radius using algebra. And by the way, if you don't like having this in a single step, you can break this algebra into more steps if you want to. It doesn't matter. But I calculate the radius using algebra, and then I just tell the user what the radius is. So let's see if this works. Volume of sphere, please. How about a volume of 10? And it tells you the radius is, 1 point something. So let's just check that. Let's see if that actually does work. So if the radius is 1.33, whatever, so, okay, so 4 divided by 3 times pi, where pi is approximated to be 3.14, times this cubed. So pretty close, right? Basically 10. So this program appears to do what I want it to do. That's good. Now, at the very least, if this radius value were like 13 rather than 1.33, that would give you a red flag that you've done something wrong, probably in this line of code here, right? Because the radius of a sphere is always smaller. No, I shouldn't say that. But if the volume is 10, you would expect the radius to be smaller, right? Because the volume is 4/3 pi r cubed. If the volume were a fraction, then you might get something else, right? But in this particular case, the physicality of the situation jives with what the program gives us. So let's just run one more, right? When we write a successful program, let's revel in it, right? We're so pleased that it's doing what we want, okay? So there you go. Volume of sphere being 13 gives you a radius of about 1.5. Okay, so in this video, we now are comfortable with, where is it? Okay, we're now comfortable with these operations, right? Division, this percentage symbol, square roots, powers, and doing things like a plus plus, a minus minus, a equals a plus 7, whatever. We're comfortable with all of this now.